Section 6.6, derivatives of implicit functions. We are going to do a few very easy, quick examples in this section. Well, let's look at this. The first example, gxy equal to 0 has a solution y equal to f of x. So if you plug this in there, it will come out. And there's a condition given that partial g partial y is not equal to 0. So now let's figure out another function f that we don't know what it is, but we will set gx equal to f where you plug in x for the first position and f of x right here in the second position. So you come up with a new function, but we don't know much about it. However, we are supposed to show the g prime of x equal to this particular relationship. Now to do that, we will first go from here, okay? So we will do gxy equal to 0, plugging in y equal to f of x. We have g of x f of x equal to 0. And that equation stands for all x. So let's take the partial derivative with respect to x in this thing, okay, with respect to x variable. So we have g1, that's with respect to the first one, plus g2 with respect to the second position, and then you have to take the derivative of the inside composite rule. So f prime of x, that equal to 0. Okay, which from here it simply means that f prime of x then equal to negative g1 over g2. 1 g2. Okay. And then the next thing we will do, so then next we'll take the derivative of this thing. What is g prime of x? G prime of x is, we'll take the derivative of this one, same principle, is equal to f1, okay, with respect to the first position plus f2, and again, we'll multiply by the composite rule f prime of x, which is, then we substitute f prime in here, which is equal to f1 plus f2 times the negative g1 divided by g2. There's a g here. Anyway, so this relationship here, as you can see, is exactly this one right here. So we're done with this problem. The next problem we do is, suppose we have an equation f x y z equal to 0, and then which is solved by x in terms of y and z, y in terms of x and z in terms of x, y. So the whole thing goes right through and is totally solvable. Okay, and so we want to show this particular relationship is equal to -1. Now you have to understand the context where this thing, what does even mean. Partial x, partial y is taken in this particular condition, and the y and z is taken from this formula, and then c to a partial x is taken from this formula. That's how you can even make sense out of this stuff. Okay, but having said that, okay, we will take the partial let's figure out what partial x partial y is. To do that, we will plug this thing in here. Okay, so then we'll write that down for once. F of x equal to f y and z, and then y and z equal to 0. And you take the partial derivative of all the stuff. Remember that x is a function of y. Sorry, that's y, that's not x. This, because f is a function of y and z. Okay. Y. Okay. So then to take the partial derivatives of all the stuff, we're plugging x in here with this relationship. So we have, so take f1, okay, and then we're taking with respect to y, because that's what we're looking for, this thing. So taking f1, and then and then times, the f is just x, so then we write down partial x, partial y. Partial x, partial y is the same as partial f, partial y. It's just the notation, because x is the same as f. So So we'll just write it down this way. And then with respect, since we're doing y, so then next, then f2, there's a y there. So then we just have 2. And partial y by partial y is just 1. And then z is a constant for what we're concerned because we're only taking it with respect to y. So there's nothing else left. So this whole thing will be equal to 0 because the original equation is 0. And similarly, we will do the same thing with y and z in exactly the same way. So now the next thing we'll do is plug in the y equation in the y position and take derivative with respect to z. Now if you do that, you have you plug this thing in with respect to z, you have so then x become you have let's see, y and z. If you then you have x and z in here. So then the first position becomes, which is the constant. Okay, the first position is just x since we have, so that is going to be the constant. And the second position you have x y equal to y of z, so we will have f2, okay, because x is a relative constant in here because we're only doing y and z, so we will ignore f1, and then f2 plugging in the y, then we have partial y, partial z, because y is the same as g, okay, and then plus f3. Let's see, f3 is just z, and since we're taking partial with respect to z, that's just 1. So it will have just f3 and left. So that's that. And then lastly, we'll do the same thing as plugging in z in here, which is xy, and we're taking partial with respect to x. To do that, we have the same deal, and then we have f3, and then, pardon me. Since we're plugging in z in this position and taking partial with respect to x, so then we will have left f1, which has x, okay? And then plus f2 is a y, and since we're taking with respect to x, we don't care about f2, because f2 is just going to be 0. And then f3 has z in it, so we have f3, and then partial z, partial x. And that will be equal to 0. Now from that we get, from this thing we get partial x, partial y equal to minus f2 over 2 over f1. This is the same thing. And then partial y, partial z equal to minus f3 over f2. And then lastly, partial c, partial x equal to minus f1 over f3. Now we are trying to show that these three things multiplied equal to -1. Now if you look at this thing, there's 2 over 1, 3 over 2, and 1 over 3. If you multiply these three things together, everything will cancel each other out, and all you got is 3 negative signs left, which results into 1 negative sign. And that concludes our problem.